All right, and we're going to extend our knowledge of the fundamental theorem of similarity here in lesson 12.5, where we're going to find some missing values of similar figures based on volumes, areas, and lengths. So a couple of examples here to talk about. Our first example here is that we're searching for Bigfoot. Scary. And you know that the average person is 5'9" and has a footprint area of 77 inches squared. So if you see a footprint, as we've all seen footprints in the mud or the snow or wherever, that average footprint area is 77 inches squared. And let's say that you find a footprint that has an area of 150 inches squared. And we want to estimate the height of what we're suspecting is Bigfoot based on the person or thing that made this footprint. So we're going to compare a couple things here. We're comparing a length, because a height is a length, to an area. Footprint is an area. So here's the average person who is 69 inches tall. 69 inches is 5'9". And then we have the footprint, which is 77 inches squared, and that's made as a rectangle because it's going to cover an area, and that's from 77 inches squared. So here's the average person, 69 inches tall. Their footprint is 77 inches squared. That's the footprint area. And then we have this larger footprint of 150 inches squared. That's what we found. And we want to find out, well, how tall do we suspect that this person is based on the information that we know? That the average person is 5'9", and then we know that this is inches squared, and then we can figure out how these are related by the scale factor. So we can figure out that whatever this height is, this height times the scale factor, k, is going to be the height of Bigfoot. So we need to figure out exactly what k, or the ratio of similitude, or scale factor is that relates to these two. We don't know what k is, but we can find out what k is based on the footprint area. But the footprints are measured in areas, so we need to make note that these two things are not related by a scale factor of k. They're related by the scale factor of k squared because they are areas. So 77 times whatever k squared is going to be 150. So we have this equation we need to solve for k, so we can find out what k is. So solving, we divide both sides of this equation by 77. So therefore, k squared is going to equal 1.94805, so on and so forth, by doing 150 divided by 77. That's what k squared is. We don't want to know what k squared is. We want to know what just k is. So we have to square root this number to find that k is approximately 1.4. So what that means is the relationship of the lengths is approximately 1.4. So therefore, 69 inches times the 1.4 is approximately 97 inches. So that means that whatever made this footprint is approximately 97 inches tall. That's what we can guess based on the fact that we know that these footprints, we have those areas because we can see them and measure them, are related by the scale factor squared. Square rooting that scale factor gives us what we're looking for, which is the 1.4, and then multiplying those two gives us our suspected height of 97. So there we go from area to length. Another similar example here, suppose that we have two flags that are similar. They're 2 feet and 6 feet in length. And we know the area of the small flag is 124 inches squared. What is the area of the larger flag? So similar type example here where we have the lengths, and now we want to find the areas. So the same thing, this whole fundamental theorem of similarity is going to come into play again. So here are two flags, similar. One's larger than the other one, one's smaller than the other one. 2 feet, 6 feet, based on the lengths that were given. Therefore, we can figure out that the scale factor here is going to be 3 by looking at this. I have some other information here. This 124 is the area of the small flag. The small flag is this, and the large flag has area of x. That's what we want to find. So therefore, 124 times the scale factor squared, because it's an area, is going to be the area of the larger flag. We don't know what k squared is, but we can figure out what k is because 2 times k is going to be 6 because these are lengths. Therefore, as I said before, k is going to be 3. So our scale factor, our ratio of similitude between these two flags is 3 because 2 times 3 is 6. And I can do that because the 2 and the 6 are lengths. They're not areas, they're not volumes, they're lengths. So 2 times 3 is 6. So our k is 3. Therefore, this area needs to be related to the larger area by the scale factor squared. Scale factor squared here is going to be 9. So if we do 124 times 3 squared, or 9, we're going to get 1,116 inches squared. So therefore, the area of the larger flag is 1,116 inches squared by finding the scale factor between the two flags and then squaring it because the areas are related by the scale factor squared. Another example, 16-inch pizza costs $13.50. What should a 10-inch pizza cost if we're going to use this knowledge of the fundamental theorem of similarity? If all things are fair, if it's the same deal, what would it cost? So here are two pizzas. We have a 16-inch pizza and a 10-inch pizza. We want to find out what that cost is going to be. The larger one is $13.50. We want to find this value here. So we're going to do $13.50 times k squared, because we're talking about areas here. And we know that 16 times k is going to be 10, and the 16 times k is going to be 10 because we're doing k and not k squared, because the 16, it's a 16-inch pizza. So 16-inch pizza is a length. Inches is a length, not inches squared. It's not inches cubed. It's just straight inches. So 16 times 10 is going to be, or 16 times k is going to be 10. Solving for k, we get a scale factor of 0.625. So our scale factor is 0.625. That's what's relating these two pizzas together. That's the scale factor going from one to the other. I'm going to do 1350 times 0.625 squared because the 1350 is paying for the whole area of the pizza. That's what you're paying for. The 1350 covers the whole area. When you pay 1350, you don't get inches, you get an area of the pizza. We're going to do 0.625 squared because we're paying for the pizza. 0.625 squared times 1350 is going to be approximately 527. So in all fairness, if these are the same deal, you're paying the same amount for the same amount of pizza, this 10-inch pizza should be 5.27. So we found our scale factor of k, we squared it because we're talking about areas here, and we multiplied that by the known value to get the missing value. Now we got a volume one here. So we have two statues that are similar with heights of 8 inches and 20 inches. If the larger one's 22 pounds, what's the smaller way? And the weight is a volume idea. Weight is an actual volume. Weight isn't a length. Weight isn't measured in length. Weight isn't measured in areas. Weight is measured in volumes. So we have a statue here, just making it a rectangle for the sake of simplicity. Height of 8 inches. And we have another one that has a height of 8 inches, and the weight right here is 22. So we know the two heights, 8 inches, 20 inches. We can pretty easily find our scale factor, our k, because we're relating the two lengths. So to do that, 20 times k is going to be 8, or you could do 8 times k is 20. Either way would work. I'm going to do 20 times k is equal to 8, and find that k is 0.4. So if I'm going from the larger to the smaller, if I do 20 times 0.4, I get 8. That's our scale factor. I want to find the weight of the smaller statue since these things are similar. Weight is a three-dimensional idea, an idea of volume. So what I have to do with the scale factor here is cube it, do 0.4 to the third power, and then multiply that by 22, the known volume. So 22 times 0.4 to the third power is going to be the volume or the weight of the smaller statue, which is approximately 1.4 pounds. That comes from 0.4 to the third times 22, 1.4 pounds. is approximately the weight of the smaller statue since they're similar.